Thank you for the chance to speak here. And this is a joint result with Mert Shalom, who is now at University of Washington. He used to be my student at Simon Fraser. And it's about like classical communication complexity, I guess, as more classical than most of the talks here. There won't be much fancy things, but I still have to say what the setup is. So it's the most classical thing. It's a two-party communication complexity. There is Alice and Bob. They want to compute a function. Half of the input is known to Alice, the other half is known to Bob. And they exchange some messages. And, well, it's the randomized model, of course. And I assume they have joint random source, so for free they can use the same random source. And they want to output correct output with some probability, say at least 3/4. And the goals, so there are two goals. One is the standard goal of minimizing the communication, and the second, that may be not so standard or not as often studied, is to minimize the number of rounds. So in this number of messages they send. And well, these are conflicting goals sometimes. So you're looking for a possible trade-off between them. So if you can minimize the number of rounds without increasing the total communication, is great. If not, then there might be some kind of trade-off between them. Okay. So what are the two main examples that were studied last, 3 decades? Set disjointness and equality. So they look similar, but we know that they behave very differently. So in the set disjointness, there is the classical result of Kalina-Sundaram and Schnitger, that basically you cannot do better than the trivial protocol. One has to send the entire input. And for the equality, just 2 bits in one round is enough. So you cannot beat that. So one is very easy, one is very hard. And of course, this has been studied for so long, there is not much to say about these two problems. But surprisingly, there is something to say about close relatives of these problems. So one of the things I will say was already mentioned this afternoon. We will see that. But the main point is that we consider variants of these problems, and the first variant is of set disjointness. So in set disjointness, you have a base set, age of n elements. The players get subsets. They want to decide if they are disjoint or not. And a variant of that is the sparse or small set disjointness. It's the same problem exactly, except you restrict the input. So you say that, okay, they get subsets, but these subsets should be small. It only makes sense if they are way, way smaller than the size of the universe. And of course, I hate this arrow here. It's outside. So clearly, if you want to decide the disjointness on a k-size universe, that's contained in this problem, and the full disjointness problem on size n universe is also contained in it. So the complexity, therefore, of the sparse set disjointness, well, it's at least omega of k from the lower bound, at least at most order of n from the upper bound. That doesn't mean much, but even the trivial protocol is better than that. It's k times log n. So if k is much less than n, then it's already better. You can even get k log k bound with the trivial reduction of the size of the universe. You can assume that the size of the universe is, say, quadratic in k. And then this became, so all these are one-round protocols. So you can solve sparse disjointness by one-round protocol with, say, k log k bits. And so this is the theorem that that was already mentioned this afternoon. Hastad and Wigderson proved that, well, actually you can do it in order of k bits. So this log factor is not needed. Date is a bit funny. I mean, they actually announced it like 10 years earlier, and then this is when it was published. So, okay. So this is optimal. I mean, obviously I cannot improve on this result because this is optimal. So what can I add? So first, when actually Mert was starting to work on this, he wanted to, consider the other parameter that I mentioned, not just the communication, but also the number of rounds. So what if you want to minimize the number of rounds? And then, so if you also consider that, then this is the original Hastad-Wigderson protocol. So it's order of k bits, which is optimal. It has log k or order of log k rounds. And they proved a constant error. That's not a big deal. I mean, they could have proved exponentially small error too if they wanted. But this is how our result compared to it. We decrease the number of rounds substantially from logarithmic to log star. So log star is how many times you apply log to kill a number. And exponentially small error. So this is, it's nice. I mean, we don't pay anything for reducing, so there is no trade-off yet. We went from logarithmic number of rounds to log star rounds, and we didn't have to pay for that. But the important, or the hard part here is to prove that this is actually optimal. You cannot go below log star without paying for it. And
there's nothing less than log star.
Oh yeah, because there's no well, constant is less than log star, right? Well, I mean, I can come up with like square of log star or whatever, but the constant is that's an interest. I mean, okay, so that's where interesting trade-offs comes in, and that was the mathematically hard part of our result, is to prove that log star is tight, and this trade-off that I will show is also tight for any number of rounds below log star. But we also found something funny or whatever, something that is nice, and that's this. That the Hastad-Wigderson protocol just gives a 0-1 output, and that's what's required, right? I mean, you ask whether two sets are disjoint. I mean, they are either disjoint or not disjoint. That's a 1-bit output. But with tweaking our protocol, we can actually output the actual intersection without paying more. So it's still order of k bits and log star k rounds. You can ask how I can output an intersection when even outputting it is more than order of k bits. So if the universe is like huge, intersection can be like size k half. So I mean, that's kind of cheating. It's not the output. I mean, the players will know. I mean, for them, it's not a big deal. I mean, they already have a size k set that contains the intersection. So for them, it's just order of k bits to know what is the intersection. They will know. I mean, for an outsider looking at the transcript, they cannot possibly know because the transcript is too small to tell the entire intersection. But that's still nice. I mean, the players themselves will know the intersection. Okay, and this is the trade-off that I said we had. So imagine that you have R rounds. R is now less than log star, so it's better to think of R as a constant because, as we know, there is nothing less than log star but constants. And then you will have to pay for that. Instead of k bits, you will have to pay k times R times iterated log of k in communication for that. And that's also optimal. So for any given R, this is optimal. So it's a theta, actually. So you see that where the log star coming from, I mean, if you put log star here, then this is just a constant. And therefore, you are still at order of k. And if you want to make this as a lower bound on the number of rounds, if you insist on order of k bits, then you get that log star minus order of 1 is the correct answer. Of course, if you put log star minus 2 here, then it's still order of k. That's fine. Okay, so that's the tight bound. So this has 3 parts, basically. One is this free reduction on the number of rounds. That's really very easy. It's just a 1-sentence trick. This nice observation that you can actually find the intersection, that's another idea, but I can hopefully convey that. And the mathematically deepest part is, of course, in this lower bound, and I will show the least of that. I try to, and I have some slides on that, but I won't have time to go into the details there. Okay, so before we do that, I want to go back to the Hastad-Wigderson protocol. It's a very nice and simple protocol, and that's what we use. I mean, our contribution for the upper bound is just a very small, tiny tweak in this protocol. So this is the protocol. Alice has X and picks a random set S0 that contains S. I will tell you later how she picks that. Sends that over. And now they know that the intersection must be inside this set because, well, X is inside this set. So Bob will know that the intersection is actually in the intersection of his set as an S node. Clearly, wherever if there is an intersection, it must be in this. So his next message is just a random set containing that. So this random set S1 will contain the intersection. He sends over that message, and this kind of repeats. So now Alice knows that the intersection is, well, in S1 and in her set, and finds a random subset containing that, sends that over, and so forth. Where does it end? So these are the sets sent over back and forth, and they stop if the current set is empty. So the current set is all the so for Alice, the current set is all the intersection of the sets that were sent back and forth, because they all contain the intersection plus the intersection of X also. If that happens to be empty, then she knows that there is no way there is anything in the intersection. Intersection must be empty. So they stop and announce that the sets are disjoint. And this is a one-sided error thing, so there is no error in this announcement here. And otherwise, they just stop and say intersect if they run out of time. And they can run out of time in 2 different ways. Either the number of rounds are exhausted, so instead of order of log k, I should specify like 100 log k rounds. Nothing happens, then they stop. Or if like 200k bits are already used up, then they stop. So that's the protocol, but I didn't tell you how these random sets are selected and sent over. Obviously, you don't want to send the entire set. So these random sets are coming from the joint random source. So there is like a list of random subsets of age. These are uniform, independent random subsets, and whenever somebody has to send a random subset containing something, he or she will send the next random subset in the index of the next random subset that is good, that contains. So for the first set, Alice has to pick a set that contains X. Well, he looks at the first index such that that indexed random set contains X. And the good thing is that the expected number of bits she will send is exactly, well, approximately, or expectation, it's the size of X. I mean, any random set will contain X with probability, well, 1 over 2 to the size of X. So in probably one of the first 2 to the size of X sets, one of them will be good. So she will have to send this many bits. So what happens is, well, I already told that this is a one-sided error protocol, so no error for intersecting sets. So we only have to worry about disjoint sets. So imagine that there are 2 disjoint sets, X and Y are disjoint, and then whenever messages are sent back and forth, what you expect is that this current set is halved. I mean, you just get, basically, you intersect it with a random set. And a random set will, in expectation, halve the size of your current set. So, of course, you have to bound the error probability, whatever, but on a high level, it's clear that for most of the time, in low k rounds, you will arrive to the empty set. And where the first round you already used up k bits, then the second round you already using up k half bits because your set is already half that big. So there is like an exponential decrease in the bits you use up in every round. So altogether you just use up order of k bits. So that's the Hastad-Wigderson protocol. So I promise that low k expected round and low k and k bits. So our tweak on this is just a very small tweak. We use biased random sets. So instead of taking a random set that is a uniform set, we take a random set that is not uniform. It is a small set, which is achieved by taking every element independently with some probability p. And p will be very small. And that's good on one side because it's quicker in decreasing the. So if I give you a random set with this bias p there, and you're intersecting your own set with that, then from size k you go directly to size p times k in expectation, which is that's good. If p is small, that's much less than k half. But you have to pay for it. It's harder to find. So whenever I'm sending a message that's like a random set containing my current set. And if my current set is X, then I have to wait longer before I find a set that contains it. And this is how much you have to wait. So this is how many bits you will send in expectation. And the good thing is that the thing that you gain is p, and the thing that you pay for is just log 1 over p. So that's kind of the exponential advantage. So as your sets get closer, smaller and smaller, you can afford very high, much higher bias. Every round, your bias will be p that is smaller and smaller, and that's the optimal trade-off. Every next p will be exponential in the previous p, and that's where log star is coming in, and the iterated log and everything. So that's just the high-level overview, but this is basically everything there is to it. So by tweaking the protocol with these biased random sets, again, you are not paying for those random sets. They are coming from the joint random source, so they are free. You're only paying for finding the first one that is good for your purposes, and well, there you pay this much. So this is the tweak on the Hastad-Wigderson protocol that reduces the number of rounds, and of course it also gives you the trade-off. If you are willing to send a bit longer messages, then you can start with a very small p already in the first round, and then a constant number of rounds will be enough. So it gives you all the upper bounds that I mentioned, and really there is not much into it. So this is actually this appeared in, I guess, in Fox 13, I guess. But back then we didn't know that we can find the intersection, so that came later. But that's very nice. So I will tell you how to find the intersection. So the trick is that, well, the non-trick is that you try to do the same thing. You try to send, forget about the bias, you're just sending back and forth these random sets containing the current set that is containing whatever can be still in the intersection. And why is this infeasible? Because so it almost works, but here is the problem. So that's the universe, here is X, here is Y, and there is this big intersection now. So this can be size K or K half or something. And whenever Alice sends a set that will contain X, so it will probably halve the rest of the Y. But the current set will always include this intersection. So you can't use the so the number of rounds will be the same and whatever, but the rounds will be longer. You cannot really expect an exponential decrease in the size of the current set, because now the size, that size will never go below the size of the true intersection. So it looks like a problem. And the good part is that, so there is this true intersection part. This is the intersection of X and Y. And the rest will really decrease as you would expect. If you don't do the biases, then it will basically halve every time. So whatever you have outside the true intersection, that behaves nicely. So what you have is that if you look at Alice's view of the whole thing, so he has her set X, and after like 10 rounds he still has this very big set remaining. So the next set will probably not halve it, because it's probably most of it is already the intersection. So she knows what to expect. She has a lot of information about the next set coming. She knows how much it will cut away from her set. And we can use that. So we can use that the decrease, we know that the decrease will be small. So after a few rounds, what you have is almost the intersection. There are just a couple of more elements that you have to get rid of. So every set that cuts off more than that is not very likely that it will be Bob's message. So what Bob will do is she'll look for the next random set that contains his current set, but sending the index over would be a waste. It's too long. So he just sends a couple of bits from the index, and that will be enough for Alice. She will know that, okay, so this might mean a couple of possible sets that Bob really meant, and she will go for the one that cuts away from her sets the smallest amount, and that will, with high likelihood, it will be correct. So we can kind of maintain that the message size is not corresponding to the entire intersection, but just the part of the Alice's current set that is not the true intersection. So that's the protocol for finding the intersection. Well, the sketch of the protocol anyway. And just a few words about the lower bound. Before we go to the lower bound, there is this related problem, the equality. We know that it has a 2-bit single round solution, but there is a version of that, the exist equal problem, which is a parallel repetition version of that. So or direct sum version if you want. So Alice gets like k inputs, Bob gets like k inputs, and they want to solve the equality problem for all of them. Well, they don't really, they just want to solve the OR of this problem, of this k equality problem. So they have a large string. Alice's and Bob has also a large string, and they want to decide if there is at least one position where the two strings are equal. And that's a special case of sparse set disjointness. So you can build this set of pairs. Alice can build a set of pairs. Bob can build a set of pairs. And the equality happens if these two sets are not disjoint. So solving this sparse set disjointness problem solves the exist equal problem, and you have the same bounds. So you can solve it with log star rounds and order of k bits, or even fewer bits with some iterated log extra cost. And this is still optimal for NER. And I'm telling you this for two reasons. One is because all the lower bounds are for the exist equal problem. And it's a direct, where is it? So it's an elementary argument for single round protocols. You get that k log k of basically the trivial protocol is optimal, and the round elimination argument in general, and that involves entropies and mutual informations and whatever. But the most important part is an isoperimetric equality on the Hamming cube. So you are asking for like the most compact set, but the way we define compact is not standard, so we kind of had to build that isoperimetric inequality ourselves. So this is how we measure compactness. So take a random ball, so with a fixed radius but around the random point, and intersect it with your set. Take the logarithm of that and take the expected size.
What is t? T is some fixed temperature? What is t to the?
T, so when you take t is the universe for the equality problem. So when you take the exist equal problem, you have this n, that's the important parameter, how many equality problems you have to solve, and there is another parameter, how big those equality problems are.
So the number of, or you had or of k questions before.
Or of, yeah, so k is n. K and n are the same.
And t is?
T is just the universe for the equality problem. So a ladder for the equality problem is coming from a universe of size t. So maybe I should have wrote like n to the k, and then it's more consistent with what I said earlier.
Here the average is over x as in h, I suppose. Here the expectation is over x in h.
Here the x in the entire Hamming cube. So that's a grid. It's like a t by t by t by t grid. And your averaging is over the entire grid.
But you want to make sure that this is never empty, right?
Yeah, well, maybe you add +1 too. Yeah, you're right. If it's 0, I took the logarithm of 0, and that's a big no, I shouldn't have done that, but it's basically good.
What's the radius of the ball?
So the radius of the ball is depends on, so that's a fixed parameter, so it's fixed for the entire, it will be basically proportional to the dimension, like n over 100 or something like that. Anyway, I'm running out of time, so I just have this.
Question: What are the things that actually achieve that? So
we didn't really solve the isoperimetric inequality. We have a lower bound that you cannot be more compact than the number. But what is the most compact? That depends on how big the size is. Sometimes it's a face of the cube, so you fix a couple of coordinates. Sometimes it's the opposite, like the complement of that. I mean, it really changes, and we didn't find the optimal solution.
It's never like the Hamming ball itself. It's sub.
No, it doesn't tend to be the Hamming ball. It's more like you fix a couple of coordinates and. So, but this is a nice observation. It's not very surprising, but I finished my talk with this. It was a bit surprising for us. So you can solve a single inequality problem with 10 bits in a single round. Maybe you want to still use a single round, or maybe just like a bounded number of rounds, like 3 rounds. And because of a lower bound, you need more than, so you want to solve the OR of k equalities. And the direct sum question is how this relates to like k times. Is it smaller than, you need really k times that much k times that much communication or not? Turns out that that's not the right question. You need more than k times that much. For 1 round you need k times log k bits. For 2 rounds you need k log k bits. And well, that's not really surprising, because if you really solve that with 0.1% of an error, if k is large and you solve each instance with that much error, it kind of adds up, and there will be an error somewhere. So, I mean, if you want to solve it in 1 round, then you better solve it with order of 1 over k error, and then suddenly solving a single problem takes log k bits, and it's k log k. So it's just surprising that it's more than a linear increase for linear number of repetitions. Thank you.
Okay, are there any questions?
Yeah. What happens in the case of 0 error? How does your result compare to Hasper results? Expected communication.
0 error expected communication. So I think it does. I mean, it does work with 0 error. I mean, not the finding the intersection part doesn't, but just reducing the number of rounds, it works the same way, I think. For the finding the intersection, there will be all kind of errors coming in when you didn't guess right which message was sent. I mean, Bob sent some set and you didn't guess right which set he sent. Then all kinds of error come in, and we cannot make it 0 error.
Okay, let's thank the speaker.